So welcome for today's lecture, and our today's lecture is on the UV visible spectrophotometry. Okay, so whenever we say UV visible spectrophotometry, the picture comes to our mind is that there should be a light involved. Either it can be a visible light or it can be a ultraviolet light, right? So light can be different type based on wavelength of light. Okay, so why this ultra visible visible spectrophotometry is important for us? In our biochemistry lab, when we say UV visible spectrophotometry, we have estimations, right? We have biochemical estimations. We have to estimate the glucose, we have to estimate the lipid, SDL, LDL, we have to estimate the magnesium, calcium, phosphate, sodium. So these things, the protein, this thing we can estimate with the help of the UV visible spectrophotometer based on the principle of the light. And what is the principle of the light we can use in the UV visible spectrophotometry? So we have simple principle here. So we are going to depict it here. So UV visible spectrophotometry, right? So we have this light source here. So this is a polychromatic light. Polychromatic light means that light is made up of multiple colors. So when we say we see white light, this white light can be divided into 7 colors, right? Like our rainbow colors, it can be separated into 7 colors. So whenever there is clouds and sunlight passes through it, it gets split into the 7 colors. Likewise, we want to split our light into a particular color, and particular color has a particular wavelength. So what is that? So this is a polychromatic light. For example, polychromatic light, we are passing it through the monochromator. So monochromator can either be a prism, which is made up of quartz material, or it can be made up of this grating thing, right? Grating. So monochromator can be a prism or grating. So we are passing this monochromator light through polychromatic light through this monochromator. Now this is incident light. And now we have our sample. For example, glucose we want to estimate, and this glucose sample we have kept in this cuvette. Okay, so this is a cuvette, and this dot 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 black dot, this is a glucose, and we want to estimate how much concentration of the glucose is there in our sample. So if we want to estimate the concentration, we have incident light and we have transmitted light. So whenever we pass the light through this sample, some light get absorbed in our sample and other light get transmitted. Okay, so this is a not absorbed light, this is incident light and transmitted light. Okay, so this one is the incident light is coming here, something is getting absorbed and then it is getting transmitted. So that is why we have I0 as an incident light and I as a transmitted light, and this we are detecting in this photodetector. The photodetector can be a different type, like photomultiplier to photovoltaic cell. So these are the different equipments which can measure the light intensity. It can convert it into the electronic current motion, and then it can be measured based on how much light is falling on the detector. We can see the intensity of the light. So that is a detector. So this is our principle of spectrophotometer. So incident light, transmitted light. Now how to measure concentration? So for measuring concentration, so this part is over. So concentration measurement. So next we have incident and transmitted light. So there is a formula for this one. This is I is equal to I0 raised to I0 multiplied by 10 raised to minus epsilon C lambda Cl. Epsilon is a molar extinction coefficient. Molar extinction coefficient. C is a concentration. L is a path length. Here. L is a path length here. So we have molar extinction coefficient, which is a specific for specific chemical. For glucose it is specific, for protein it is specific. So molar extinction coefficient based on solution, concentration and path length. So we have this equation, I is equal to I0 multiplied by 10 raised to minus epsilon c lambda. So I divided by I0. So we have I is equal to I0 multiplied by 10 raised to minus epsilon c lambda CL. So we take this I in the downside. I divided by I0 is equal to 10 raised to minus epsilon CL. So we have, if you want to get rid of negative sign, we can take invert it. I0 divided by I is equal to 10 raised to epsilon CL. If you take logarithm of this one, log to the base 10, I0 by I is equal to epsilon CL. So this epsilon CL is basically absorption. So absorption is equal to epsilon CL, which is equal to log to the base 10 I0 by I. So based on this equation we get absorption is directly proportional to CL. So this L is a path length of this cuvette. So this cuvette, every time blank standard test we are using same. So if absorption becomes directly concentration to concentration. So this one is a Lambert-Beer law. So Lambert-Beer law says that absorption is directly proportional to concentration and the path length. Okay, so this, as the concentration increases, this absorption reading increases. And for light, so this is equation A is equal to ECL. And this one is a wavelength. So distance between the two crests is a wavelength, and this height is a amplitude. One is a crest, other is a trough. So this light is a electromagnetic wave. So waveform distance between two crests is a this one. If we are plotting wavelength on the x-axis and the absorption on the y-axis, we can see this is our absorption. So this absorption, if it is increasing, it is a hyperchromic shift. If it is decreasing, it is a hypochromic shift. If it is shifting on the right side, it is a red shift. And if it is shifting to the left side, it is a blue shift. So basically this absorption as a optical density reading, we can use in our biochemical calculation to calculate the glucose concentration, right? So that was about our UV visible spectrophotometry.